Chapter 6, Shared, Thermochemistry. All right, what do we mean by thermochemistry? We have an idea of what chemistry is. Thermo just refers to heat. And that's in particular. In general, we're talking about energy transfers. And usually we account for energy transfers in chemical reactions by a measure of the transfer of heat. So we know that energy itself, in other words, the whole universe is made up of one of two types of things. One is matter, of course. Anything that has mass and occupies space is matter. But the other thing occupying our universe is energy. And energy is defined in terms of a capacity to do work or to produce heat. Right, so now we're saying energy could be something other than heat. And in chemistry, we primarily focus on heat, but not exclusively. In this chapter, we are going to focus exclusively on, and I should say, we're going to spend most of our time on heat. We will have to introduce energy as a topic a little later on, and you'll see when that happens why we need to do that. This law is not really new, but it's still valid. And it just says that the law of conservation energy is that energy cannot be converted, cannot be created or destroyed, but it can only be converted from one form into another. And this actually is a statement of the first law of thermodynamics, which simply says that taking the whole universe together, that's the first law of thermodynamics. For the whole universe, the change in energy is zero, which just means that you can convert it, but you can't create it or destroy it. All right. In most cases, a chemical reaction is accompanied, actually physical processes too. Chemical and physical processes rarely occur without some transfer of energy. There's got to be a reason for a chemical reaction to occur. And usually we can identify that reason as what is the energy state of the system before and after the reaction. If the system after the reaction is at a lower energy state, then there is sufficient drive to go in that direction for the reaction. That's the primary motivation for chemical reactions to occur. They can go in the other direction, but if they do that, they have to be forced. So I'm talking about spontaneous reactions. Spontaneous reactions don't occur spontaneously unless there's a reason. Now, sometimes there is no obvious exchange of energy, but the reaction still occurs. So we have to explain that. And that's where the second law of thermodynamics comes in. And we're not going to talk about that today. We're just talking about transfers of energy in a chemical reaction. All right. We can subdivide energy into two types: potential energy and kinetic energy. Potential energy refers to a couple of different possibilities. It means exactly that. It's potential. In other words, it's not realized, but it's in there and available, or some of it is available. It may be due to position. Right? If I climb a 10-story building, I am storing up energy in me as a result of my position above the surface of the Earth. How do I get that energy back? Jump off the building. If I jump off the building, I'll get that energy back when I hit the ground. So that's energy, potential energy of position. In chemistry, we have potential energy of composition. And that type of energy is due primarily to, in chemistry that is, primarily to the energy of bonds that hold atoms together. Now there are other types of compositional potential energy. One is electrostatic. And that is due to, in chemistry, transfer of electrons. If you transfer electrons from one place to another, then you get an attraction based upon electrostatics. Or you may even get a repulsion. But those are the two types of potential energy: positional, compositional. Kinetic energy is even simpler than that. Kinetic energy is due entirely to motion. Any mass, no matter how small, if it's moving, has kinetic energy. And we can calculate the kinetic energy. Based upon the object's mass and its velocity. So notice that the kinetic energy of a moving mass increases linearly with the mass. In other words, if you double the mass and you don't change anything else, velocity is the same, then the kinetic energy doubles. But if you double the velocity for the same mass, then you have quadrupled the kinetic energy. A practical application is how much energy do you have when you do you have to add to your car to go from versus 0 to 30 or 30 to 60. The amount of energy required to go from 0 to 30 miles an hour is 1/4 of the energy required to go from 0 to 60. So that's why as you speed up, as you increase your speed, the amount of energy given up when you come to an abrupt stop, say in an accident, is much higher the faster you go. So your chances of being injured with your speed increasing go like that. The faster you go, you get a chance of injury is much, much higher as you speed up. Now, the kinetic energy of molecules or any type of atoms or molecules in motion can also be related not just to linear motion, which would be the primary energy form for molecules in a gas moving, because they bounce off of each other, but not very often, versus solids. A solid has kinetic energy, but it's kinetic energy of vibration. So the molecules inside a solid will vibrate, and their motion goes back and forth. So that complicates things quite a bit. Those are the two types of energy: potential, kinetic. Now, when we transfer energy from one object to another, if the collision is elastic, if it's an elastic collision, then all of the energy of object A will be transferred into object B. A will stop, B will continue on with the same amount of energy that A possessed. Now in this case, B is at rest and A has potential energy of position because it's higher than B. Okay? So when A comes to rest at B's position, it should transfer all of its energy of position to B. And that transfer is in the form of kinetic energy. So B will acquire motion based upon the energy that was released when A dropped from A to B's position. So we would expect that B will travel all the way up to the same height as A. That's conservation of energy. Here's what actually happens. The collision between A and B is not entirely elastic. In other words, a 100% efficient transfer of energy does not occur. So we end up with B at this lower level. So if energy is conserved, where did the energy go between B, where B is now, and where we expected it to be? Because that's a difference in energy there. So where's that energy? It's in heat. Friction, which can be defined in several ways, like friction with the surface upon which A and B roll, or internal friction. So when A and B smack together, the compression causes molecules to move past one another, and that causes friction and consumption of some of the energy and release as heat. And heat is always measured as temperature change. So what I'm saying is, if I jump off that 10-story building and I land on the ground, then where's that energy going? Well, some of it's going to go into my broken bones and disrupted organs. But some of it's going to be converted into heat, because all of that energy has to go somewhere. Now, if the collision is completely inelastic, that is, I drop something off the building that's kind of malleable, it's like Play-Doh, and it acquires the energy from that height, when it hits the ground, it splats. Now, in that case, all the energy from the top of the building to the ground is converted into heat. And if you stick a thermometer in there that's very sensitive, you can pick up a change in temperature inside that object or inside the ground immediately where it hit. Okay. So that's reality. Let's clarify the difference between temperature and heat. They are related, but temperature is an intensive property, which means that as long as the object is uniformly distributed in energy, then the temperature will be the same no matter where you select to measure it on that object. Its intensity. The amount of matter doesn't matter. Whereas heat is always measured as a transfer of energy, and heat itself, just as heat, is a capacity factor. In other words, the amount of heat does matter how much material you have. So if I have an object this size and it's at a certain temperature, and I have an object that's this size, a bigger size, and it's at the same temperature, the bigger object contains more heat energy. That's what I mean by it. That's a capacity factor. Temperature is an intensity factor or property. And in fact, temperature is proportional. That's what that squiggly means. Temperature is proportional to the average kinetic energy of the molecules in the object. That's what that bar on top means. It means average. Although this type of average needs some explaining at some point in the future. I think actually in the second semester we get into that. But for now, that's a good enough definition. The average kinetic energy and temperature are proportional. Temperature is a measure of the average kinetic energy, which means that all the molecules in the object are not moving at the same velocity. Right? They don't all have the same kinetic energy at the same time. It's not just a point. It's a spread. Okay. So how do we measure heat? The only way to measure heat is by measuring the transfer of energy from one object to another, and they have to be at two different temperatures. So if this object is at T2 and this object is at T1, and the temperature T1 is greater than T2, then you will get heat transferred between T1 to T2. Heat, it always transfers from higher to lower temperature. So you're probably wondering, well, how does air conditioning work? Right? Because it's going the opposite direction, isn't it? On a hot day outside, it's cool inside. Should be the other way around. Well, in that case, you couple two processes together. And the air conditioning unit transfers energy from a high temperature compressed gas. Well, actually, it's a liquid then. And when that gas expands, it cools. And when it does that, then it absorbs heat from its surroundings. And if those surroundings happen to be in your house, then your house is cooled down. But the heat that is picked up by the air conditioner is dumped at higher temperature into the outside air. So it's always high temperature to low temperature heat transfer. Okay. So I need to define some other terms. What is work? Remember we said energy is the capacity to do work or to generate heat. So if we can get work, we need a definition. All right, so I have to go back to physics for this one. Work is actually a force that is applied over a distance. So if I apply a force against something and it's moving a certain distance, then I have done that much work. It can be measured. So the force in SI units is a Newton. And the distance, of course, is meter. So work is Newton meters. And work is a measure of energy. And the standard unit of energy is a joule. So a joule is equal to 1 Newton meter. All right. So what if I stand up against a wall and I push on it with a force? The wall doesn't move. Have I done any work? Nope. I have expended energy. So where does that energy go? As I'm pushing on the wall heats up. I am adding energy to the wall, but I'm not moving it. So I haven't done any work, but I have expended energy. Right? All the energy was converted into heat. All right. Now this is important, but it may be a little hard to grasp. Energy is a state function. What do we mean by state function? State function means that whatever we define as energy, doesn't matter how it got there. It just is right now. Its present state. That's energy. Whereas work and heat are path functions. Energy is a state function. Work and heat are path functions. It does matter the path that was taken to define work. Work is easier to understand, right? Because if you add energy to an object by pushing it up an inclined plane, right? You're going up this inclined plane and you're applying a force, and you go a distance, right? So when you get to the top, well, I should have started at the bottom. Let's try that again. All right, so let's say we're starting right at the bottom. We apply a force, and we go that distance. Okay, a force applied over that distance equals the work that I've done to get it there. Okay. What if I take an indirect route? In other words, instead of a straight inclined plane, I have a corkscrew, and I just push it around that corkscrew all the way up, but it's shallower, right? So it goes like this, and I get to the same point, right? The work that was done is different this way than it is that way. Simply because it took me longer to do it. It took a longer distance to do it. Similarly, heat is also a path function. So the route you take matters. It's a path function. And it does depend on where you started and where you end up. That's the difference between state and path functions. Right. Some functions are state functions, and some are path functions. Energy is one of them. We'll come back to that topic. Now, we need to define some more terms before we can talk intelligently about this transfer of energy and heat. We have to define what a system is. There are two things always in a discussion. If you say one, you have to say the other. One is system. Actually, system is whatever you define it to be. And then everything else is surroundings. Right? And there's a boundary right here between the system and the surroundings. So things happen across that boundary. Okay, so there's our systems, there's our surroundings. We, however, can make modifications so that where we would normally consider surroundings as the rest of the universe, we can modify things by the way we construct it and define three other types of arrangements, right? So if the system is open, then you can transfer energy and mass or matter backwards and forwards freely. That's an open system. Now, a lot of systems in the universe are like that, but they're difficult to study. There's no control. You can't, it's hard to measure what's happening. So sometimes we have a closed system where matter cannot move. So once you establish your boundaries, whatever matter is in there stays there, and whatever matter is out here stays here. Okay? Oh, by the way, you may also be able to separate your system and surroundings from everything else so that you can also define how much of the universe is your surroundings. Okay, and then for the third one, if that boundary here will not allow energy to transfer either, that system is said to be isolated. Right there. That's an isolated system. We use isolated systems very often in thermochemistry to investigate chemical reactions. And I'll show you, I hope I have time today, I'll show you how that works. Let me check something. Hold on a second. I want to see how much time I've got and if I can pick it up again on, yeah. Okay, so I don't have to finish today. We've got Wednesday, I can finish this discussion. So I'll pick a convenient point. I have a feeling we're not gonna be able to finish it today. So I'll pick a point and then we'll pick it up again on Wednesday. All right, so we have system and surroundings, and then the system's relationship to its surroundings can be of these three types: open, closed, isolated. All right, so let me redraw this thing. We have our system, and then we have our surroundings. And we describe happenings, phenomena, in terms of how the energy is transferred across that boundary. And everything is referenced in terms of the system. So if energy, heat flow, I should say, if heat flow is into the system, and this would be our chemical reaction taking place, if it draws energy from the surroundings, then that is an endothermic reaction. And any quantitative value that we give to it must be preceded by a positive sign. Right? Everything's referenced to the system. If the system is receiving something, it's positive. Okay? If it goes the other direction, if heat flows out, it's exothermic. And the value is preceded by a negative sign. Now we use a symbol, abbreviation for heat in these terms. We say it's Q. So Q is our abbreviation for heat. If it goes in, if Q is positive, it's endothermic. If Q is negative, it's exothermic. Now the other condition is any energy that is gained by the system must be lost by the surroundings. So if we were to say something like this endothermic reaction allows the system to absorb 10 kilojoules, right? Then the surroundings must lose 10 kilojoules. Okay? So let's see if we have a grasp of the obvious here. Is the freezing of water an endothermic or exothermic process? First of all, define your system. What is the system? System is the water that's undergoing the phase change. Right? So we have water here. And the surroundings. So if the water is freezing, what's happening to the energy? Right? In order to freeze, the system has to lose energy, does it not? It has to get cold. So if it loses energy, this process is exothermic. Okay? Let's look at these examples. So in this case, the system is underlined for you. So you don't have to guess, or you don't have to define it yourself. Let's say your hand is the system, and it gets cold when you touch ice. Right? So what's the process here? Energy is leaving your hand, is exothermic. What if the ice gets warmer when you touch it? Now the ice is the system, and the ice is receiving energy, which is an endothermic process. So it all depends on the definition of your system. Yeah, I'm going to leave that up there. How about water boils in a kettle? So the water in the kettle is the system, and if it's going to boil, what do you have to do to it? You have to add energy. That's an endothermic process. What about water vapor that condenses? So if the water is phase change from gas to liquid, it must lose energy. That's an exothermic process. Ice cream melts, right? We add energy to the ice cream and make it melt. It's endothermic. Okay. Now, let's see. In this case, we need to define our system and the surroundings. Then we can say what direction the energy is. Methane is burning in a Bunsen burner in your lab. So what's the system? Well, if your burner has a flame on top, right? And it's got gas coming in here. So what happens before it can burn? It has to be mixed with air. So we mix in some air, and the methane is coming in here. And then up here, the flame is the system. The burning methane is the system. And if we define it in those terms, then you just get close and you can feel the heat coming off of it. So it's exothermic process. Oh, it's going to let me answer it. Okay. Okay, water drops sitting on your skin after swimming evaporate. This word problem says that the water drops evaporate. So that's a clue there. The water drops are the system. They must absorb energy. It's an endothermic process that causes the water to evaporate. Okay, so now let me make room. Let's write this in terms of a chemical equation. Hydrogen gas and oxygen gas. Hydrogen gas is like this. Oxygen gas is like that. And it yields what? It yields water. Well, let's keep it simple. If we do it that way, then we've got to account for a phase change too. So let's keep everything in the same phase. Right? It's so hot that the water is still vaporized. Now, in this process, we know that energy is released, right? All you have to do is watch a space shuttle go up, and you know hydrogen plus oxygen yields lots of energy. So it's exothermic. in addition to the fact that exothermic means a negative Q, where would it be positioned in this equation if we considered heat as either a reactant or a product? If it gives up heat, then it ends up over here. Right? So the Q is actually a product. Now, if we look at it that way, then it's easier to determine which is higher in energy, this side or that side. Well, that is lower in energy than this, right? Because there's the energy, there's the heat. It was stored as potential energy in the chemical bonds here. And then it was released when we created water, and now it's over here. Okay? So which is lower in energy? The water, of course. And that's one of the driving forces of the reaction. All right, so here we have a restatement. Thermodynamics is the umbrella discipline for thermochemistry. Thermochemistry is a subset of thermodynamics. And it's a good place to start. I mean, if this is your first exposure, thermochemistry is the best place to begin because it's a lot simpler and in many ways easier to understand. All right. So we've got our system. We've got our system there, and of course surroundings everywhere else. And we can define this system in terms of its total amount of energy, everything included. We call it the internal energy. So it has a certain amount of internal energy. That includes the kinetic energy and the potential energy of everything in the system. Okay? The thing is, we never measure absolute values because we don't know where the 0 point is, or we can't use the 0 reference. For instance, absolute 0, the Kelvin system, right? That's a theoretical 0. We can never actually measure it relative to that 0. But once we get up high enough in temperature, we can measure relative differences in temperature. That's possible. We do the same thing with energy. We actually measure a change in internal energy. While the E itself does mean all the energy of the system, we really don't know what it is. We can only measure it in terms of a change in internal energy. And that internal energy change is due to two factors. Any change in heat that the system has acquired or given up, and the other factor is the work. Was there some work done on the system, or did the system have to do work on its surroundings? That's how we define internal energy. Q is relatively easy to measure, just a change in temperature. W represents work, and that one requires some special thinking. The best way to think about doing work on a system is start with gases. Right? Why? Because if you press on a liquid, you may have force, but the liquid's not going to move. There's no change in volume. Solids are even worse. But when you press on a gas, you do get movement. Right? So you can measure the compression of a gas as force times distance. Okay. And remember, I mean, this hasn't changed from the very beginning. When we measure and express these quantities, they always consist of a number. Actually, there are three parts: a number, the units of measure, and the sign. The units of measure eventually are joules, but we may have some intermediate steps. But the sign is always there, and the sign is important because it tells you what direction is it going. Is the work going this way? And it's the same for work as it is for heat. If you're doing work on the system, it's positive. If the system is doing work on the surroundings, W is negative. Right? Same sign convention for Q and for W. All right. I just emphasize this point again. It's always reference to the system. Right? We mentioned this before. Q is positive for endothermic, negative for exothermic. Similarly, work, right? If you're doing work on the system, it's positive. If the system's doing work on the surroundings, it's negative. Okay, I got a little video for you to watch. This for a little over 4 minutes. This is Professor Dave.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released, but it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension.
He's introducing some terms here that we haven't covered yet, so don't panic. We're gonna work on them. I couldn't find a better place to insert this video. We'll do some of those calculations as well.
Thanks for watching, guys. Subscribe to my channel for more tutorials. And as
Okay. So he mentioned a term, delta H, enthalpy. Okay, set that aside for just a minute, and let's talk about the work function of delta E. So we're going to look at this one right here. How do you determine work? And as I said, the most convenient way is to start with gases, because you can do work on a gas, and the gas then would be the confined gas would be the system. And if you can do work on it, it's easier to measure, right? So in this cylinder, we have a gas, and we can either compress it or allow it to expand. So if we compress it, that is, the surroundings now are doing work on the system, and W is positive. If we allow the gas to expand under a constant force, then the gas is doing work on the surroundings, and W is negative. Right? So how do we measure that? Well, first of all, we define some terms. Right? This pressure on the gas is defined as force per unit area. Right? So there's your F value, the force. This delta H, the difference in height, is our D value, or the distance traveled. So what's the change in volume? Well, we have a definite area here that doesn't change. So the area times the height is the volume. So in the process of either doing work on the surroundings or having work done on the gas, we have changed the volume a certain amount over that distance, and with a constant force, right? So in that case, we just need to do a little manipulation here. Pressure is force per unit area, and force rearranged is pressure times area, right? So we have another way of expressing the force, pressure times the area. The change in volume is the distance traveled, or delta H. In this case, we changed it to D, times the area. And the distance traveled is the change in volume divided by area. See where I'm going with this? Now work is force times distance, or this force times that distance, or this expression times that expression. And when we put those together, we find that work on a gas can be expressed as pressure times a change in volume. Okay? Let's see. I don't think that's saying anything new. Yeah, okay. So for an expanding gas, a change in volume is positive because the volume is increasing. And if we plug that change in volume into the expression times a constant pressure, we have the wrong sign, right? Because when the volume is expanding, the gas is doing work on its surroundings, which means the work is negative. Right? See the problem? our convention says that work should be negative. But if we plug a positive value in here and a positive value in there, we get a positive value, which runs counter to our convention of work done on the surroundings is negative value. So we have to put a fudge factor in there, which is a negative sign. That's why work measured in with our present convention as expressed in a gas is negative pressure times a change in volume. Notice that if we say work equals minus P pressure in atmospheres and volume in liters, we get minus liter atmospheres. That's not joules, right? I mean, it is an expression of energy in terms of work, but it's not interconvertible until you use the conversion factor. 1 liter atmosphere is equal to 101.3 joules. Right? So that means, right, we have an equivalence, we've got a conversion factor. So 1 liter atmosphere per 101.3 joules. Right? So if you have joules and you want to convert to liter atmospheres, multiply it by that. If you have liter atmospheres and you want to convert it to joules, flip it and then multiply it. Okay? So which of these following performs more work? A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. All right, so the work in the first example is going to be what? A gas is expanding, right? So that means it's doing work on its surroundings, which means W is negative, and the pressure is a constant 2 atmospheres. What's the change in volume? It's final volume minus initial volume. 4 minus 1. So that's 3 times 2 is minus 6 liter atmospheres. We're going to leave it like that because the second question uses the same units of measure. As long as we got the same units of measure, we can make a side-by-side comparison. So that's A. How about B? W equals a gas is expanding. Okay, we got another negative. It's doing work on the surroundings. Pressure is 3 atmospheres. And a change in volume is final 3 minus initial 1, which is 3 minus 1 liters. So that's 2 times 3 is 6. They're exactly the same. The same amount of work is done by each gas on its surroundings. All right. I'm going to leave that one up there. Okay, well, let me change this right here. Because now we're focused on delta E. What is the sign of delta E for each of the following with the listed conditions? All right. So A is what? A is an endothermic process, endothermic, that performs work. So that means it does work on its surroundings. And does work on its surroundings. Right? So what will the signs be here? Endothermic means energy is being absorbed by the system, has a positive sign, while this one does work on its surroundings is a negative sign. Okay. Now, for this one, for the first choice, the absolute amount of work exceeds the amount of heat transferred. So this value, work, and that's what those two lines mean on either side, absolute. It means drop the sign. So the absolute value of work is greater than the absolute value of heat. So this one is greater than that one. So when we add them together, delta E is what? If this one's bigger than that one, then delta E is negative, right? What if heat is greater than work? If that's greater than that, now the delta E is positive. Okay? Let's see, do I have that? Yeah. What if work is done on the gas? Endothermic processes, work is done on the gas and the process is exothermic. Exothermic. And work on the gas. Right? So now the work is positive. It's being done on the system. And exothermic means it's negative. Okay, that's B. Now what's delta E? Well, if the work term is greater than the heat term, then delta E is positive. But if the work term is less than the heat term, or this is greater than that one, then delta E is negative. Okay? All right. Now we're going to talk about enthalpy. The first thing to recognize is that delta H and Q are different values. In some respects, they're related because they do talk about heat energy. But in the first place, Q is a path function. It does matter how you get from point A to point B. Whereas delta H is a state function. It doesn't matter how you get from A to B. We think of delta H as more a potential heat transfer. This is an actual measurement, Q, of the amount of heat transferred to or from a system. And it's one of two means of transferring. Transferring energy, either Q or W, heat transfer or work transfer. And Q and W are both path functions. So that's why delta E equals Q plus W to define the internal energy of a system. Enthalpy, though, is often referred to as a thermodynamic potential. It's similar to internal energy. Internal energy is also a state function. That's kind of strange, isn't it? A state function E, change in a state function E, is equal to the summation of two path functions, Q and W. And one way to think of delta H is that it's the potential heat energy of the system, right? So that means that there's something missing between delta H and delta E are related as state functions, but delta E accounts for the heat energy potential of the system, whereas delta E includes everything. So that means that there's something else that we would have to account for to assign all the potential energy in terms of delta E. And here it is. This is one form where the delta E and the change in pressure volume of a gas combine to tell you the heat potential. So that might look strange. We're thinking that the total internal energy should actually be a sum of something other two other things rather than the other way around. But remember that these can have different signs, right? That could be a negative sign and actually subtract from delta E to give you delta H. But by the same token, mathematically, it can go the other direction. So you could add something to delta E, and then delta H would be increased. All right, so if this equation is true, where the enthalpy is equal to the internal energy plus a change in pressure times volume, then what we can do is a mathematical substitution of delta E, which is Q plus W. And then if we further process the values and we say, all right, let's suppose that we're maintaining constant pressure, which is fairly easy to do. That brings the P term outside the delta. Now P doesn't change, only volume changes. Okay, under these special circumstances. Now, if W is equal to minus P delta V, then we can substitute that in there for W. And minus P delta V combined with P delta V plus cancel each other out, and that means delta H, or enthalpy, is equal to Q in this special case where pressure is constant. If pressure is always constant as the transition takes place, then we can measure delta H simply by measuring the transfer of heat. So that's why it's useful to maintain constant pressure in the change of gas volume. Because under those circumstances, Q and delta H are equal in magnitude. Okay. All right, more time. Let's say you're studying a process and it takes place in a system that goes from pressure 1, volume 1, temperature 1, and all three change. Pressure 2, volume 2, temperature 2. It looks like we're working on gases again, doesn't it? There are lots of different paths that you can take between these two states. And in those different paths that you can take on the way from one condition to the other, Q and W can have many different values depending on the path that you take. That's why they're path functions. However, since delta H is an expression of potential heat energy of a system, how you get from one place to another doesn't concern delta H. It's simply a potential. So if you go from one position to the other in these two situations, go from situation 1 to 2, delta H will always be the same. It is a state function. Doesn't matter how it got there. And that's convenient. Because now we can determine the delta H for any reaction as long as we know the delta H that's attributed to the products minus the delta H of that attributed to the reactants. And we can calculate delta H for the reaction. Okay. So that's just a restatement of some facts. Right? So let's look at a real chemical reaction and the enthalpy assigned to that reaction. Right? So here we have C3H8, which is propane. Right? Same stuff you fire up your barbecue or heat your house in some cases. And we're going to burn it, combine it with oxygen, and make carbon dioxide and water. This reaction, as balanced, is exothermic. See that the convention for Q is the same as for delta H. If the delta H is negative, we have an exothermic reaction. And that's a lot of exothermia, minus 2,000 kilojoules. Now, this says per mole of propane. It can say that because there's only 1 mole of propane here in the balanced equation. What I like to see is if this is not there, the divisor of the quotient, then this value alone is given. That means that that value is assigned to the balanced equation as written. And that's what Professor Dave was referring to. If you double this, right, then you double the enthalpy. Right? If we put a 2 in front of each one of these, if we multiply 2 through the entire equation, then the delta H would change to minus 4,442 kilojoules. So let's use this balanced equation and see if we can determine how much energy will be released if we burn 5 grams of propane, as long as there's excess oxygen. Okay, that's a given. Okay, so here we have 5 grams. Remember, you can't go anywhere in an equation, not even outside to the enthalpy, unless you know moles. So 5 grams is converted with the molar mass to 0.1134 moles of propane. Okay, so now we know how many moles it is. We can use this equation, that relationship, to convert moles into kilojoules, and we find that minus 252 kilojoules is produced when 5 grams of propane is consumed in this reaction. Okay, that brings us to, and we got time for this, that brings us to a method that's used in chemistry to measure the heat transfer of a reaction. You know, how much heat does the reaction produce, or how much does it absorb in a process? It's called calorimetry. Calor referring is the Latin for heat, and metry, of course, is for measure. So we're measuring heat. Let's see. I got another video coming up in a second. Yeah, one more slide after this, and then you get to see Professor Dave again. I don't know if he's a real professor. It's probably, he just acquired that term. It's kind of like Professor Higgins on the My Fair Lady. I don't, he wasn't employed by any college, so I wouldn't call him professor in that realm, but everybody called him Professor Higgins. Anyway, the specific heat capacity. first we probably should define heat capacity. The heat capacity, big C, of any object is the amount of energy required to raise the temperature of that object by 1 degree Celsius. Right? So this is a capacity factor, property, the heat capacity of an object. The bigger the object of the same material, the more heat it can absorb before it raises the temperature 1 degree centigrade, Celsius. Let me check something here. 1, 2, 3, 4, 5. Okay. Right. So that has limited applicability. Right? If you have a substance, it's more important for you to know, more useful to know, how much heat is required to raise 1 unit of that material 1 degree centigrade. And that unit is usually grams, but sometimes moles. So specific heat capacity is given a small s, and its units of measure are joules per gram degree centigrade. Right? The amount of energy to raise the temperature of 1 gram 1 degree Celsius, or sometimes joules per mole degree Celsius. Okay. And when you do calorimetry in the lab for this course, be careful to watch this, right? Because when we're expressing the specific heat and the transfer of energy for, say, an acid-base reaction, where one is neutralizing the other, it's in terms of moles of water produced. So be careful. One or the other, not both, but one or the other is operative. Okay, so this specific heat capacity is an intensity property. In other words, it doesn't matter how much of the substance you have, so many grams, so many moles, it's still the same value as long as you have the same substance. Okay, and that tends to be more useful. So plain specific heat capacity is usually grams. If we specify molar heat capacity, then we're referring to this one right here. Okay. If 2 reactants at the same temperature are mixed and the resulting solution gets warmer, this means that the reaction is releasing energy from its system to the surroundings, which is the water or the environment, whatever it happens to be. It may not be water, but whatever. If the surroundings increase in temperature, and if the mixture of your reactants increases in temperature, that's exothermic, and the delta H will be negative. The other way around. If it gets cooler during the reaction, that means it's absorbing heat from its surroundings, it's endothermic then. And the value of delta H will be positive. Okay? I think we got another video coming up here.
Hey, it's Professor Dave. Let's talk about...
He knows a lot about science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchange is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials.
Okay, that's the way that I was taught how to do calorimetry. This side balances that side. But suppose you have more than one side, right? Suppose there's more than one heat transfer taking place in your isolated system. That's what the styrofoam cups do. They isolate the system. So now nothing crosses the barrier. Not energy, not matter. What happens in Vegas stays in Vegas. So I have a slightly different take, a different approach that is more universally applicable than just this energy change equals that energy change. Right, so we have this system, right? And this is what you will use in, or what I used in the demo that you will view on calorimetry. Except I removed the stir. I didn't use the stir. I used the thermometer to stir things, and it works just as well. I used to use a stir, but some of the chemical reactions corroded the stir that I used, and it just was too much trouble. So if you're careful, then you can use a thermometer to stir your solution. Anyway, this is an isolated system. That's important. So this is the way we look at it. First of all, this equation is correct. He used the correct equation here. And we use Q because we're actually measuring heat. We're not measuring enthalpy. We're measuring heat transfer. So Q transferred is equal to the specific heat of the substance times its mass, in most cases, times the change in temperature. And the change in temperature is always final minus initial, even if it gives you a negative number. It's always final minus initial. That's absolutely essential that you get that right. Okay. So here's what I use. Since this is an isolated system, no energy goes in, no energy goes out, no matter goes in, no matter goes out. So whatever happens inside that isolated system is equal to 0. Overall, inside the isolated system, there is no energy, there is no heat change. All right? There is transfer within the system, and that's what we're getting at. So if one part of your system makes this change, and another part makes this change, and another part makes this change, on out to however many parts you have, then all of those changes together has to equal 0 because the system is isolated. Okay? Now, you just need to define which one of these is which. Okay? Now, we'll come back to that. First, I want a little intuition to be operative. And we're coming down to a point. Yeah. We'll do the next 3 slides and then we'll stop. And we'll pick it up Wednesday with the last of my Professor Dave videos as we get into Hess's law. So let's just look at this and say, intuitively speaking, if you have 100 grams of water at 90 degrees Celsius and you add it to 100 grams of water at 10 degrees Celsius, what will be the final temperature? If you have equal amounts of water, right, then they should meet in the middle, right? So what's the middle of 90 to 100? 10 to 90, excuse me. It's 50 degrees, exactly 50 degrees. Okay? So the heat from the 100 grams of this water partially transferred to a 100 gram sample of this water. And since they're both the same heat capacity, the temperature change met in the middle. So what's the final temperature for both sides? 50 degrees. What's the change in temperature for the 90 degrees? It goes from 90 to a final of 50. Final minus initial, excuse me. 50 minus 90 would be 40 degrees. Whereas 10 goes up to 50. 50 minus 10 is 40 degrees in the other direction. Okay? But suppose you have different amounts of water, right? So what's that formula? Q equals S times the mass times the change in temperature. And water was 4.186, I think, as its specific heat. So one of these, Q1, would be the specific heat of water, joules per gram degree C, times mass. So the first one would be 100 grams, times the final temperature minus the initial temperature. What's the final temperature? We don't know. We don't know yet. It's unknown. What's the initial temperature for 100 grams? 90 degrees. Okay? How about the other one? Same specific heat. Let me see if I got that right. I'm working from memory here. And it doesn't say yet. Professor Dave may have said that's probably, maybe I don't remember it. So what's the mass here? 500 grams. Same final temperature, right? When they come to equilibrium, temperature-wise, they're at the same temperature, right? So the final temperature is the same for both. But this one started off at 10 degrees, right? So if you do this calculation and add it together with this calculation, they should be 0, right? So that plus that equals 0. With one unknown, you can solve it. But intuitively speaking, should the temperature be greater than 50 or less than 50? Well, you've got 500 grams here at 10 degrees, but only 100 grams at 90. So I would expect the temperature to be less than 50. Between 10 and 50, right? This is going to heat up a little bit. This is going to cool down a lot. So what's the final temperature? Well, if we do that calculation, put those two terms, that one plus that one, equals 0, and then solve for the unknown, you should get 23 degrees. Try it out and see. Okay, here's another. We're complicating things a little more. So we're in the styrofoam cup with 50 grams of water at 10 degrees, and then you have an iron ball at 90 degrees. You put them together, right? 4.18 for water, specific heat, and 0.45 for iron. So now you have to substitute a different value in for S for the iron. So the second one would be iron. Let's see, we'd have 50 grams here. For water, and final temperature. Okay, so that's still unknown. And for the water, the starting temperature is 10 degrees. Right? For the iron, you have a different value, 0.45. It's specific heat for iron. Now the iron is starting off at 90 degrees. With a final temperature, and the iron ball weighs 50 grams. There you go. Now, we can calculate the final temperature because add these together is equals to 0. But what do you think the temperature would be? How much heat is contained in the 50-gram iron ball? Is it greater than or less than the amount of heat in water? Specific heat tells you that with the heat capacity of 0.45, it takes about 1/10 as much heat to increase the temperature of an iron ball. That is, it does for water. So when you put them together, the temperature is probably going to be less than 50 degrees. Right? Because the water temperature won't move as much as the iron ball will move. So it's going to be on the side toward the water. And that calculation will give you 18 degrees Celsius right there for that unknown. Okay? All right. So let's see. We got a couple of minutes. So we'll just outline what Hess's law is. Hess's law takes advantage of the fact that enthalpy, delta H, is a state function. That means it doesn't matter how you get there. And Hess surmised, that's a real person, Hess surmised that you could calculate the delta H for an unknown reaction as long as you had known reactions of defined enthalpies. So, in other words, say we want to know, you have a reaction down here, final, and we want to know what the delta H is. We don't know. You suspect that that reaction might be explosive or might be hazardous in some form due to the amount of heat that it would release. So you say, it'd be nice to know, you know, if that reaction is going to be dangerous. So you say, this reaction, I could take this reaction, and this reaction, and add them up. Left side, right side of the arrow, add them up, and I end up with the final. And each one of these has a delta H. As long as I manipulate these reactions in such a way that they add together to the final reaction, then I can add the changed delta H's for each one of these to that final one. That's Hess's law. Okay, so I'm going to stop here, and we'll pick it up here on Wednesday and finish out this chapter. And I'm finished a little bit early because I need to, actually. So let me make a mark, and actually I'll come back to this very slide on the 10th of March. Okay? Any questions before we depart for the day? I think I'm right, 3:45? Yeah, okay. I'm gonna stop the share. There we go.